Hello, everybody. Welcome back to EM378 SI Online. We have I think, a pretty full video today, so we'll get right into it. It's our last week of SI, so we have a WebEx Tuesday and a WebEx Thursday. You know the times, and potentially I'll be holding an exam review over the weekend, similar to what we did for Exam 3, where I post in a mock exam and then some questions and then the solutions on YouTube. Not sure exactly what that would look like just yet, but stay tuned for that because I think the exam 3 was really helpful. I got a lot of views um, on those videos. So yeah, if it's helpful for you guys, we'll do that. All right, so on to the final exam. This week we're going to be doing final exam review. That's going to be the focus of it. All right, so what we're going to do is, as we're going through the week, we're just going to hit one or two of these problems every single day. So today we're going to be doing force on a plane and manometer. But they're just kind of more review problems. They aren't super in-depth. So this shouldn't be the end-all be-all of your studying. So in the final exam, the nice thing about Schaefer's exam is it's 6 questions, and there are 7 different types of questions we've done this semester. And the final exam just kind of picks 6 of them and then goes for it. It's definitely going to have a force on a plane problem, a Bernoulli equation problem, and that'll include all of the different terms that are there, loss, friction, all that stuff. A control volume, the one where you have to get like a nozzle or something. Then you have forces and whatever. So like one of these. Pi terms and modeling. We just did that. Drag and lift is something we're starting to go over now. That one's pretty straightforward. It's mostly just plug and chug, which is nice. Same with open channel flow. He's going to go over this maybe 1 or 2 days, and you'll be like, how are we going to have an exam question on this? But honestly, once you've done 1 or 2 problems, you've done all of them. So all the ones that I've starred, those you can pretty much guarantee are going to be on the exam. And then the 6th one, maybe a manometer or a pi term kind of a thing. At the same time, I'm not really sure. Maybe he'll switch out, combine a manometer and Bernoulli and go with like a pi term. I don't know. He'll figure it out. But I would say as long as you need to know how to do these 7 things, you're going to do great on the exam. So on that note, we're going to work on a couple problems today. First one we're going to do is a manometer problem. A pretty simple one, but just as kind of a refresher. So we have this piston with a cross-sectional area of 0.07 meters squared on the cylinder containing water, as shown in the figure below. An open U-tube manometer is connected to the cylinder as shown for H1 equals to 60 millimeters and H equal to 100 millimeters. What is the value of the force P? I renamed that F when I was doing the problem because pressure and P, anyway, force F, acting on the piston. The weight of the piston is negligible. All right. So we know we have this force here creates a certain amount of pressure right there. And then that pressure is somehow translated through the fluid up over to here to this pressure. All right. So what we do is we start at pressure 1, which is 0.1. I'm going to call that pressure at the piston. And then, so that's our starting pressure. And then we're going to kind of snake our way through here, right? So as we're working our way through the problem, we're going to go down in water, depth of H1. And whenever we go down, we add, right? Because as you go deeper in a pool, there's more pressure on your ears. So as you go deeper in the fluids, there's going to be more pressure. So go down H1, and our fluid is water. So gamma of water. And then what we can do is we can go down here, then go all the way up here, and then come back down here. But the net result of that is just coming straight across to this point here. So we're going to go down here and then kind of just translate over to this point. This point and this point, same pressure. Right? No matter the shape of the object, parts of equal depth in the fluid are going to have the same pressure. That's not true if the fluid changes or anything like that. But if you're in the same fluid, right? This is all water. If they're at the same depth, then they're going to have the same pressure. So now we're over here, and then same principle applies. Here and here have the same pressure. So then we can just kind of ignore this U-bend and then just go straight up. So since we're going up, we're going to subtract. So minus H in mercury. So gamma Hg. And then where do we end up? Where we end up is going to be the right-hand side of the equation. What's the pressure at this point? Since it's open to the atmosphere, we're just going to go with gauge pressure and say it's 0, which makes our lives a little bit easier. In this way, you can solve for your pressure at P. It's equal to H, which is 0.1 times gamma of mercury. Let's see, what is that? 133. And then subtract H1, 0.06, multiplied by gamma of water, 9.8. And we'll get pressure at P is 12.7 kilonewtons per meter squared. But that's not the question here. The question is, what is this force F that applies to this point? Well, to create a pressure, so pressure is force over area. So if we look at our pressure at P, we can solve this. So our F value that we're looking for is the pressure at P times the area of this piston, which we're given as 0.07 meters squared. So this is 12.7 times 0.07, and we get 0.889 kilonewtons. And we're just going to call that 889 newtons. Thinking faster than I was writing. So 889 newtons is your answer there. Again, this isn't a super in-depth manometer problem, just kind of as a refresher for you guys. But the general idea is if you go down in pressure, you add. If you come back up in pressure, you subtract. And remember, if it's the same depth of the same liquid, doesn't matter the shape, you're going to have pressure at same pressure at the same depth in the same fluid. All right. And then remember your easy points that you can pick, right? Like this pressure right under here, and then open to the atmosphere is 0. So you kind of work your way on the left-hand side, and wherever you end up is your right-hand side. All right. So second problem that we'll do is we're going to do a force on a plane problem. All right, so we're looking for the weight needed to hold the wall shown in the figure below. The wall is 10 meters wide. All right, so what I'm going to do is I'm going to draw a free body diagram of the gate. So at the pin, I'm going to call the pin O. So I have a pin OY, pin reactions OY, OX. I have this tension created by the weight here. Call that force of the weight. And then I have some water here. And then I have my resultant force from the fluid at some height h from the bottom. Right? We'll kind of give that a solid line. So there's our free body diagram. And so we're solving for this. And we don't really care about what's happening at the pin. So we know we're going to end up doing sum of moments about O is equal to 0. And I'm going to call that positive. Because that way we only have two things that we need to solve for, which is the resultant force and this height h. So for our resultant force, that's just the density multiplied by gravity multiplied by depth to the centroid. And that's the centroid of our object of interest. So it's not the centroid of the wall. It's going to be the centroid of this portion of the wall, right? Only the part that's submerged. And then multiply that by area. This is the same as gamma HC times area. So we know we're working with, since we know we're working with water, there's our density, there's our gravity. And so this is a rectangular wall, right? Because we're given a width and we have this right here. So we can kind of imagine it going into the wall or going into the page where our width is that way. So the depth of the centroid here is just going to be halfway down since it's a rectangle. So our HC is 2. And then our area is the area of contact between the fluid and the wall. In this case, that is 4 times our width of 10. Plug all those numbers into your calculator, you'll get 785 kilonewtons, which is a pretty big force, but that kind of makes sense. All right. So the other thing that we need is this height here. And if you remember how this force is kind of acting, right? It's like it's a distributed load triangularly, where it starts at 0 here, right? Because there's no fluid putting the force on. Well, there's air, but we can kind of neglect that because there's, right? Since we have equal and opposite reactions on either side here, we don't have to care about the air. So starts at 0 here and it gets all the way down to some depth here. But just to find the resultant of that, we already found the resultant of that. And then we found the resultant of that, but the location of the resultant is just going to be a third of the way from the height of our distributed load. So it's going to be 1/3 times 4. Just put that in as 1.33 meters. All right. So then we look at our free body diagram. We see our sum of moments is going to get us the answer that we want. So I'll write that down here. Sum of moments about O, which is our hinge, is equal to 0. And that's force from the weight multiplied by its height, which is 7, and then minus Fr times H. So then we get the force of the weight is 785 times 1.33 divided by 7. 149 kilonewtons. And so then we get that our weight, once you do that conversion there, should be 15,219 kilograms. If I did the math right there. All right. So, we'll just leave the weight in kilonewtons. You can put it into kilograms if you want, but that'll be our answer there. All right, guys. That was our first bit of final exam review. If you have any on this list that you particularly want to see or want me to spend a session on later this week, either the Tuesday or the Thursday one, reach out. You can send me a message through the SI website, or you could also leave a comment down below this YouTube video. Either way, I'll see it and I will plan accordingly. See you guys on Tuesday and Thursday, and maybe for the exam review on the weekend. Have a good one.